Hi, I'm Michael Woods, Chief Scientist at the Asian Turfgrass Center. Yesterday, I gave a presentation to about 50 golf course superintendents from Thailand at Thana City Golf and Sport Club in Bangkok. The topic of the presentation was understanding data use for turf management, and I talked specifically about a certain type of data because when I think of data that we collect on golf courses or on turfgrass sites, there's really two types. One type is evaluating the performance of the turf, measuring how the ball will bounce and roll across the surface, for example, using a stimp meter or a Clegg hammer or a true firm. Then there's another type of data that we collect, and that type of data is involved with predicting how the grass will actually grow. So in the presentation, I talked about that type of data. When we look at turfgrass growth or plant growth in general, we can look at it as sort of a model of photosynthesis, and we can look at what really affects the growth. And when we simplify it and look at what really affects the growth, what affects how the grass will grow is the temperature, the amount of water that's available to the plant, the amount of photosynthetic light, and the amount of nitrogen that the plant has available. In the presentation, I didn't talk so much about temperature because in Thailand we're dealing with warm season grasses. And in Thailand, the average temperature only varies by 3 or 4 degrees throughout the year. And the temperatures are always quite close to an optimum for warm season turfgrass growth. So in the winter time in Bangkok, the temperature gets a little bit cool and the grass will grow a little bit slower. But basically throughout the year the grass can grow at close to an optimum rate. And for nitrogen, I didn't talk so much about that either because we don't really collect so much data on the plant nitrogen status. Usually we just modify the growth by applying light amounts of nitrogen when we want to stimulate the growth. So I focus more on the meters that we can use and the data that we can collect to evaluate the plant water status, which is essentially because the plant takes the moisture up from the soil, so what we do is we measure the amount of water in the soil. And then also I looked at meters for measuring photosynthetic light. Starting off, I talked about the soil moisture content and how we can use meters to measure that. Last year I was in India and it was interesting. We went to a golf course, and at that golf course we had the soil moisture meter with us, and there were some areas on the greens where the grass was not performing as well as it was on other areas. And when we measured the soil moisture in those areas, it was very, very low. It was less than 10% soil moisture. And in fact, here's one of the soil cores. We pulled it out from one of those areas, and we actually found that the soil was hydrophobic, or that it repelled water. You can see the little water droplet there that has failed to penetrate into the sand because it became so dry. And I explained that we can use soil moisture meters to make sure that we keep the soil moisture within a safety zone, that we keep it above that critical moisture content of maybe 7% or 8% or 10% or whatever it is on the low end that can cause the soil to become hydrophobic. I visited another golf course in Delhi, and we also saw, as you can see there's a bit of thin area on the turf, and when we checked it, we found that those areas were hydrophobic also and that they were quite dry. So in the extreme case of having soils that are too dry, soil moisture meters can help you to identify that. But ideally, the soil moisture meter would be used to make sure that you don't let the soil get that dry. So as the soils start to approach that point where the grass can wilt or where the hydrophobic conditions could start to occur, water could be applied before that happens because the soil moisture meter can help to identify that. It's common now for golf course maintenance at the tournament level and also for the everyday maintenance. It's common to use soil moisture meters. And this tweet was just a few days ago. This week actually is the Players' Championship at TPC Sawgrass, and I thought it was interesting to see that the the course maintenance team there have shared this information, and they said their target today is 18%, and they're just right on it. So it's really standard to use the soil moisture meters to try to get the soil moisture content at just the right level, both for plant health and growth and also for playability. And the playability is affected by how much moisture is in the soil, because if the green is very wet, it's going to be softer, there's going to be more ball marks, there's the potential that the mower might sink in a little bit and give a poor quality of cut. There could be more disease also. So for a number of reasons, it's beneficial to keep the soil moisture content as low as possible, however, not letting it get too low. And soil moisture meters are a great way to do that. There's an interesting article that you can find on the USGA website about how the greens were hand watered at the 2012 US Open at Olympic Club in San Francisco. And there they measured the soil moisture content, they checked different zones of the green, and then they put a flag in the green to indicate at different zones whether the soil moisture content was adequate and no water was required, or whether some supplemental water should be applied in that area. Now, you saw at TPC Sawgrass, they said on the day that they posted that photo, they had a target soil moisture content of 18% by volume. And this article on the USGA website said here they were trying to maintain 20 to 22% soil moisture, which would be enough to get through the day without wilting, and then they could check and rewater again in the evening. So keep in mind what those numbers are, because we'll return to that a little bit later. This is an example. I've just overlaid these lines over an image of the 7th green at Pebble Beach, but this is an example of how one might divide a green into zones, and one could check those different zones of the green and determine if extra water was required in different zones of the green, because it's natural for the soil moisture content to be variable and for the different amounts of water to be required in different areas of the green. So in order to achieve consistency, it's useful to break the green down into zones like this. As a summary of the soil moisture data that I've collected 1,554 individual measurements of soil moisture content using both the theta-probe and the TDR 300 probe from greens in many different countries and with different grasses. And the median value that I've measured is 25.7%. And I think that's kind of interesting because it's a little bit high. And if you look at what they're doing at TPC Sawgrass, they said they had a target of 18%. At the US Open, they were trying to have 20 to 22%. And I've seen at a lot of well-managed golf courses, it's common to have soil moisture content at, let's say, 20% or a little bit lower. So it's interesting to me that the median value that I've measured in over 1,500 measurements is above 25%. And that's an indication that there's something in the soil. These are almost all sand-based greens that I've measured from. So it's an indication that there's something in the soil that's holding more moisture, or the greens are just supplied with a little bit too much water. Now, I think it's an indication that as greens age, organic matter accumulates, and that organic matter starts to hold water. It's interesting to note also that in the United States Golf Association, the USGA specification for putting green construction, the capillary porosity of the sands that are going to meet that specification will be from 15 to 25%. So if you build a green that has a sand that meets the USGA specification, the water holding capacity will be less than 25% by definition at the very start. And it's interesting to me that more than 50% of the greens that I've measured, at the time I've measured them, they're holding more water than what that USGA spec sand could possibly hold. So it's interesting to look at what the targets are and also what the reality is, and I think that a soil moisture meter is an extremely useful tool, and I think ideally every golf course superintendent or turfgrass manager would have access to one for regular use. Moving on to the next thing I talked about, which was light, and specifically the photosynthetic irradiance, or the photosynthetically active radiation. So the grass can't use all of the light that comes from the sun or from another source, but it uses a certain fraction of that, which is the photosynthetically available light. And recently there's some meters that are available that are easy to use to quickly get a measurement of the photosynthetically active radiation. This is a meter that I've taken quite a lot of measurements with, and this one is measuring the instantaneous photosynthetically active radiation. So that's expressed in units of micromoles per square meter per second, and that's the amount of photosynthetically active light that's reaching 1 square meter in 1 second. This particular meter has a maximum. Well, basically we say that in full light the maximum would be about 2,000 micromoles per square meter per second. In this meter you see it's reading 1, but that really means it's at a maximum because it displays up to 1,999, and once it gets to that level, and then it goes to 1. So what this meter is reading right now, when I was at Takitomi Island last year in Japan on a nice day at the beach, I measured at this instant, at this particular second, it's measuring maximum photosynthetically available light. Now let's look at a video, and we're going to see that the light actually changes second by second. We can see here, it's starting off, you see the value, it says 1, but with this particular meter that means 2,000. It means we've got maximum light, so we're above 1,999. And think of what might possibly be changing the light. You're going to see it's going to change from 1 and it's going to go down. And once it goes to 1,000, that would be half of available light. See, it's gone all the way down to 800. That's less 780. That's less than 50% of available light. That's about 40%. If it's at 800, it would be at about 40% of the photosynthetically active radiation of what the maximum could be. And what's blocking that is clouds. So as the clouds come over and block the direct sunlight, they block 50% or more generally of the light. And I think that's really important for warm season grasses. Now we take the every single second of light and add that together from sunrise to sunset, and we get something called the daily light integral, or the DLI. And this is another type of meter that can be used to estimate the DLI, which again, what the DLI is the total amount of light, the total amount of photosynthetically available light that reaches the surface in 1 day. So that both the instantaneous light, what we get in just 1 second, and also the DLI are interesting to know. And there's meters that can measure both of those. This is a measurement I made at Koh Samet in Thailand. This was measuring, you see, 584 micromoles of photosynthetically active light per square meter per second. So at that very second, it's measuring 584 micromoles. And if we would make a single measurement every second throughout the day from sunrise until sunset, then we could add those numbers all together and we'd get what's called the daily light integral, or DLI. And this is a chart that shows some of the, actually this is all the measurements I made in 2012 in Thailand. And this was over multiple days, and you can see from the sunrise at about 6 in the morning until the sunset just after 6 p.m. That's where the photosynthetic irradiance goes to 0, because it's nighttime and there's no photosynthetically active light. And you can see at the top bar there at the level of 2,000, which is the maximum light in full sun with no clouds blocking the light, that happens from a little bit after 9 in the morning until almost 3 o'clock in the afternoon. So we have the potential to have maximum available photosynthetically active light in the middle of the day. And so when the sun is high in the sky, we can have maximum available light, assuming there's no clouds. But look at how many measurements were made. Each one of those little black dots is a individual measurement at an individual time. And look at how many measurements within the middle of the day, from 9 in the morning to noon to 3 in the afternoon, were less than maximum available photosynthetic light. And the reason that they're less than a maximum is because of cloud cover at that time. So the blue line represents the average value for every single second of the day, the average of all those measurements. And if we add together the points on that blue line, the average, it comes to a DLI of 35 moles of photosynthetically active light per square meter per day, which is not actually an exceptionally high number. So that shows that the clouds are blocking a significant amount of light, and you can see any value less than 1,000 is less than 50% of available light at any one moment, and there's a considerable number of measurements even during the middle of the day that have less than 50% available light. So that's quite interesting, and it's especially interesting from a research perspective, probably less practically useful in any way for a turfgrass manager. But I'd like to show something that is practically useful. This is a Tifeagle Bermuda grass green at Bangsai Country Club near Bangkok, and this is some grass that was looking pretty good. And on the same golf course putting green and the same grass of Tifeagle, there was also a section that looked like this, where there were very few leaves and it doesn't look very good at all. And the reason for that was this shade. This was at a time when the clubhouse was being renovated, and there's a section near that barrier that received quite a bit of shade. And you can see the turf has changed its growth habit. The leaves and stems have become extended and kind of it scalps off, and it just, the grass doesn't perform well at all where the light is restricted, whereas out in the center of the green where there is full light, the grass can perform very well. So in this type of situation, imagine that we're trying to grow fine turf next to a permanent structure that that casts some shade on the turf. We could take one of these meters and measure in the sun. We could take the meter and measure in the shade, and we could determine the percent reduction, and we could show that it may be impossible to grow turf in that area, or we may decide we need to use a more shade-tolerant turf in that area, or in this case we can't really do anything with the building, but with the trees we could get good justification for doing some pruning or tree removal. This is a golf course in Khao Yai to the northeast of Bangkok. You can see the Tif Dwarf on that green, that's Tif Dwarf Bermuda grass, and on the one half of the green there's perfect grass cover, there's very high quality turf, and then on the side of the green that's covered with the shade so much, you can see around the edge of the green the grass has failed, and in fact there's bare areas that are just covered in sand. And I'm going to speculate here that the reason for that is because of the shade. Now we could take a light meter and place one in the sun and measure the DLI. We could take another and put it in the shaded portion of the green, measure the DLI. And I think this is a useful way to generate numbers, to generate data that can be shared with the people who in the end give the approval to trim some of the trees or to remove some of the things that cause the shade, because sometimes it's a hard sell. For golfers, you can see the golfers there have umbrellas. It's very hot, and the golfers wisely are providing shade for themselves and making it very comfortable, or more comfortable, as they're going around the golf course. And the golfers or the golf course owner, we could imagine, might like to stand in the shade. They might appreciate the shade that's thrown by the trees, but the grass doesn't appreciate it very well. Our eyes aren't very good at determining what is the the percent reduction in photosynthetically available light. But these type of meters really are. So I find it really useful to generate data with these meters to show the percent reduction and to give some justification for pruning and tree removal programs. I did a little experiment near my apartment, which is in Bangkok, and I went out on a sunny day and measured the percent reduction in photosynthetically active radiation under 10 different trees. So in full sun, they were all at 2,000 micromoles per square meter per second, and the average under all those trees was 141. So that's an 86% reduction. And in general, at midday, when I've measured in a tropical environment, somewhere near the equator, I have usually measured under trees an 80 to 90% reduction in photosynthetic irradiance from what we would have in full sun, not affected by tree shade, to when we move into the tree shade, and the photosynthetically active light goes down by about 80 to 90% based on what I've measured. I didn't. One of the reasons I record this video is because the presentation ended then, because there were so many questions about the soil moisture meters and about the data that we can collect about light. But I wanted to talk a little bit more about a couple of other data points that are useful and sometimes absolutely essential in predicting how the turfgrass can grow. One of them is salinity, and salinity can cause a big problem. If there's too much salt, this is seashore paspalum at a golf course in Thailand, and around in that low area where we just see the sand, just at the edge of the fairway, that grass has died because of an accumulation of salt as the water with a large amount of salt has moved down into that area, and the salts accumulate. This is seashore paspalum, generally considered to be the most salt-tolerant turfgrass, and even seashore paspalum was killed because of the very high accumulation of salts. So if we have a salinity meter, we can measure the amount of salt that's in the water. And if we know how much salt is in the water, and we can check that because it's not the same every day, it's quite useful to know exactly how much salt is being applied in the water, and then we can predict how much salt is accumulating in the soil. And we can also we can do various tests of soil extracts, and we can measure how much salt is in the soil also. So if we know how much salt is in the water, and if we know how much salt is in the soil, we can determine how much irrigation needs to be applied in order to leach the salts and manage the salts so that they don't cause a severe problem with the grass. Now, every grass grasses have different salinity thresholds, so I didn't talk about that. I'm not going to talk about that. That's a different subject. But the point is, if you have salinity problems, I highly recommend having one of these meters so that you know how much salt is being applied when you irrigate, and so that you can evaluate how effective leaching programs have been and how soil salinity is in the soil. Is it going up in the soil, or is it going down in the soil over time? And that can help with managing the turf even when water with some amount of salt is being applied through irrigation. Something else that I didn't talk about, but I prepared slides for, was the pH of the soil, because pH does have some influence on the growth and a little bit on disease and on soil microbial activity, or specifically I think of thatch breakdown when I'm thinking of microbial activity. Many of the people who attended the seminar yesterday have also been out to ATC's research area, which we operated north of Bangkok from 2006 until 2009. And out there we had soils of different types with pH that ranged from about 3.7, which is extremely low, all the way up to 7, which is considered a neutral pH. And for people who've been out there, they saw that we were growing so many different kinds of grass in so many different kinds of soils with a wide range of pH, and the grasses were all performing well. And I've also done research in the greenhouse with sands with a high pH, and we can find that the biomass production of the grass, in that case the greenhouse experiment was with creeping bent grass, the biomass production can be maintained at a high level across a wide range of pH. So I'm not too concerned about pH, but we need to know what it is, and we should be aware that pH does have some effect on the grass, and I want to talk a little bit about that. But we should also recognize that grass can grow well in a wide range of pH. One thing is Bermuda grass decline, and that particular disease, which can sometimes affect turf in tropical environments, especially if the organic matter builds up in the soil, and if the soils become relatively wet with low amounts of air in them, and also if there's quite a bit of shade. So you see, we go back to the type of data that we could collect about soil moisture and about photosynthetically active radiation, which could help us to create a better growing environment for turf to prevent the Bermuda grass decline disease. But pH has an effect on this also, because the disease is more severe at moderate to high pH. So I can't really put an exact number on that, but let's say as we approach a pH of 7 and above, there's a chance that the grass would be more susceptible to the disease. So ideally, we would have the pH below about 6.5 to reduce the chance of Bermuda grass decline. But that won't solve the problem, but it may make the disease less severe. And we'd also try to address some of the soil moisture issues and some of the photosynthetically available light issues if we're going to prevent that. This photo I got from Tom Cook, my professor from Oregon State University, where I went to undergraduate, and it's really a superb photo showing thatch above the soil. And thatch buildup can occur rapidly if the pH is too low, because below a pH of about 5.5, the grass can still grow, but the soil microbial activity drops quite a bit. And the thatch is broken down by microorganisms in the soil. So if we want to minimize the amount of thatch, and keep in mind in Bangkok we have a 12-month growing season, so if we had a pH that was very low, and if we had the grass growing for 12 months of the year, and if we had, because the pH was low, if we had a restricted microbial activity in the soil, it's possible that the thatch breakdown could be very slow, and we could have a lot of thatch accumulating over a 12-month period. So in order to maximize the breakdown of thatch and to ensure that the microbial activity in the soil is not reduced because of low pH, we would ideally keep the soil pH above 5.5. And so I think everybody needs to know what their pH is, and we should recognize that grass, especially warm season grasses, can grow well across a wide range of pH. So we're talking about pHs from less than 4 up to more than 8.5. We could have warm season grasses growing. Ideally, we would keep that though within a range of about 5.5 to 6.5 to maximize the microbial activity, to maximize the nutrient availability, and in the case of the Bermuda grass decline disease, to minimize the risk of that. So that's what I talked about in the presentation on May the 7th at Thana City Golf and Sports Club. And if you would like more information about that and about the data that can be collected, there's some reports that I've posted on my website, asianturfgrass.com. Thank you.